So our last unit in the Chapter 20 Electrochemistry chapter is about electrolysis. Electrolysis is different in many ways compared to a galvanic or voltaic cell because number one, electrolytic reactions are not spontaneous. They're going to require an external current provided by like a voltage source like a battery or an electrical source to force the electrons to flow in the external circuit. So they're non-spontaneous. But the parts that are the same is reduction still occurs at the cathode and oxidation still occurs at the anode. The difference primarily is that it's a non-spontaneous flow of electrons where they're forced to flow from an outside external source of energy. Now another thing that's different in electrolytic cells, they label the anode positive and the cathode negative. It's just the opposite in a galvanic cell. Don't worry too much about that. I'm pretty certain that the AP exam is sort of taking away the confusing labeling on the electrodes. But when we get to this next diagram, I'll try to explain it a little bit better. So here's our diagram. Now this is a pretty scary setup if you ask me, because this is molten sodium chloride. So there's no water involved, because if there was water, then sodium would be blowing up in the water that'd be there. So what we have is melted sodium chloride. We still have an anode and a cathode, but the big difference is that's not a voltmeter anymore, that's a source of voltage. And you can think of this as the negative terminal of the battery from which electrons proceed. So that's why in an electrolytic cell, they label the cathode negative and the anode positive. In a voltaic cell or galvanic cell, there is no voltage source. And the idea is that if electrons which are negative are headed towards the cathode, you can think of the cathode as being positive. That's kind of an artificial labeling, so you just kind of have to get used to this concept. So this reaction would not happen spontaneously. So let's take a look at what's happening over here at the anode. Remember, these are electrodes that are dipped into molten sodium chloride. Chloride ions here will give up at this electrode some electrons. And for every 2 chlorides that give away electrons, you'll see 1 chlorine molecule bubbling away with stinky chlorine gas coming out at the anode. It's obviously being oxidized. Got it straight. Oxidation is loss of electrons, and then those electrons who normally wouldn't spontaneously go through this particular source or particular circuit are forced along by the external voltage. And the electrons, maybe you can think of them as starting here perhaps, come out of our voltage source into the cathode, and at the cathode, positive sodium ions say, thank you very much. We'll pick up those 2 electrons. And so 2 sodiums will pick up 1 electron each for 2 electrons total and make liquid molten sodium form over there at the cathode. So this is how you can get sodium refined. You'll never find sodium free in nature because that sodium is so reactive. It always wants to form ions and ionic compounds with guys like chlorides and nitrates, and then it's always soluble. So it's a hard sucker to kind of find in nature. But when we create solid, in this case we'd let it cool and then it would become solid. But when we create elemental sodium, you have to do it through electrolysis. So that's pretty much it for electrolysis if it's a molten tub of molten stuff. Now when it becomes an aqueous solution, that's when things get confusing. Here is what was happening in that previous decomposition of molten sodium chloride. Summing it up, at the cathode we're collecting electrons to make liquid sodium, and at the anode chloride ions are shedding their electrons to come bubbling off as chlorine gas at the anode. In the upcoming lab we have on electrolysis, you're going to have to identify, you're going to create a couple little mini electrolytic cells, and by powers of observation you're going to have to identify what products are being produced at which particular electrode. So in this case, if I smell stinky chlorine coming off as a bubbling gas, that was chloride ions that were losing 2 electrons. Losing 2 electrons to become chlorine gas. Now, I forgot exactly the year that we created this process to purify aluminum ore, but up until that point in time, let's say it's about the 1800s, you couldn't get metals like aluminum because they were always in a form like an ore called bauxite, and no one had figured out the way to pull the aluminum metal out of there. So at that point in time, if you were royalty and wanted to have some really fancy flatware to serve, food with at your banquets, you used aluminum. I know it seems kind of funny now, but the only way you could get elemental-free aluminum, just like the only way you could get elemental sodium, is through an electrolytic process. You take an outside voltage source and force it to be formed. So one of the interesting aspects of electrolysis is that you can do something called electroplating. Back to our flatware example. Many of us are having Thanksgiving coming up. We pull out the fancy china, we pull out the fancy flatware. If you had solid silver flatware, that's going to cost way, way more, given the price of silver these days, than if you were to purchase flatware that was silver plated. The interior of it is a non-precious metal, but on the outside, somebody's put several layers of silver atoms to make it look all shiny and pretty. So this is called electrolytic plating, and what happens is that this time the electrodes are actually taking part in the electrolysis. A lot of time the electrodes are just an inert spot for reactions to happen at, but in this case they're going to take part in it. And here's a simple little example of how you could get nickel to plate out on something. So we have our outside voltage source. This cathode right here, it doesn't say it, so you may as well label it. That's probably steel. And we have a nickel anode right here, and both of these electrodes are immersed in nickel ions. So those nickel ions, what is happening over at the anode is the atoms of nickel are being forced to lose their electrons, which transfer through the external circuit, pushed along by the voltage source. And when the atoms lose their electrons, out come nickel ions into this solution. They're migrating over here because that's our negative electrode, and as they cruise over here towards this plate, this electrode made of something like steel, they will pick up the electrons coming their way and turn back into nickel atoms, but now they're going to form a thin coating on this cheaper piece of metal, the steel electrode over there at the cathode. Here are the two reactions that are happening. When you have an active nickel electrode and another metallic electrode, like steel, for example, placed in an aqueous solution of nickel sulfate. Losing electrons over at the anode, gaining electrons over here at the cathode, and again, it looks like nothing should happen, but remember, we're forcing the electrons to flow, and nickel ions in solution will plate out on the inert electrode. And that's how we could nickel plate in this case, or silver plate our flatware if that's what we wanted to do. And that way you can protect it from corrosion. Now, the cool part about electrolysis is that you can actually quantify the amount of material that you could get to plate out. And it's going to take a flow chart of logic here to show that we'll be able to take the current. Think of it as how many electrons are flowing through, the charge on those moles of electrons. We'll be able to use stoichiometry to predict the moles of the substance that's being oxidized or reduced, and then we can turn grams into moles. This is from the old textbook. So we're going to take the charge on 1 mole of electrons to be 1 Faraday. In the old textbook they say 96,500. I think in the new textbook they use 96,485. I just need you to get the process. What's important to notice is that it's going to take 2 moles of electrons. That's not 2 electrons, but 2 mole of electrons to make 1 mole of copper metal plate out. Now, don't worry about this charge and current and time. Let's go straight to a sample exercise to explain how you can calculate how much stuff in grams plated out, as long as you know the amps and the time. So here is our first and last sample exercise of the chapter itself. It says, calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten aluminum chloride if the current is 10 amps. Okay, so first thing you got to do is you have to understand that coulombs are a function of amps and seconds. So we've got to take our 1 hour of time and turn that into seconds. That's what's happening right down here. 1 hour has 3,600 seconds in it. And an amp times the seconds will give you coulombs. That's the total amount of charge. In this case, they told us we had 10 amperes. So 10 amperes times 3,600 seconds gives you 3.6 times 10 to the fourth coulombs worth of charge. Notice that we'll be using this number to stand for the Faraday constant. So another thing you need to notice is that when aluminum is plating out, it takes 3 moles of electrons. So what we're figuring out is if we know the total charge and we know how much charge is carried on 1 mole of electrons, we can find out the number of electrons that were flowing. And the way that those are connected is with the Faraday's constant, the 96,500 or 485. So here we go. We got the charge by taking time in seconds times amps, the moles of electrons flowing times the charge per mole of electrons, so that would be 1 over 96,480 coulombs, 85 coulombs. Coulombs will cancel out, and you'll find out that you had 0.373 moles of electrons that were flowing. Well, we're almost there. We've done the hard part. Now it becomes stoichiometry. It takes 3 moles of electrons to get 1 mole of aluminum to plate out. But we only have 0.373 moles of electrons. So you can set that up with this relationship. There were 0.373 moles of electrons, and for every mole of aluminum to plate out, it requires 3 electrons, or 3 moles of electrons. So basically, your moles of electrons gets divided by 3, and that tells you how many moles of aluminum you've made, and then you multiply by the molar mass of aluminum to get the grams of aluminum. So there's a variety of factors that you can see right here. We get charge, turn it into moles of electrons. We use stoichiometry to predict the moles of aluminum, and we take the molar mass of aluminum to turn moles into grams. Sometimes your problems will go backwards, give you the amount of grams that was plated out, and ask you to go backwards and calculate perhaps how long would that take if you knew how much the amperage was, for example. So the only other thing about electrolytic cells that I want to point out, and we're going to talk about this, it's not shown in this PowerPoint, is that what's ignored on all of these slides is that when it's an aqueous solution, it could be a competing type of reaction happening inside there. You could have metals or metal salts being oxidized or reduced at anodes and cathodes, or you could see water being oxidized or reduced at the various electrodes, and that depends upon their reduction potential. So what I will do is I will hold on that thought until I see you guys next, and we'll go through, especially when we do our electrolysis lab, how having water in there can kind of confuse this, trying to understand what's happening at the anode and what's happening at the cathode. But to sum up, electrolysis requires external source of voltage to force a non-spontaneous reaction to occur. Now when you log in to let me know that you saw this vodcast, I'm also going to ask you to submit your response to a very simple question when you are done here seeing this vodcast. And I'll be looking for that before class starts the next time I see you. Adios.